Good morning, class. We are looking at section 5.5, the substitution rule. Okay, there are, of course, a lot of formulas we have discussed for basic integration. And you recall the fundamental theorem of calculus, so on and so forth. So what is the substitution rule? The substitution rule, in short, is the reverse process of the chain rule. If we were to differentiate this, capital F of g of x would be capital F prime of g of x times g prime of x. And normally, you remember that we use the following notation. Capital F prime is lowercase f. So that means if I go the reverse process, anti-differentiate or integrate, I come up with the original function. And the original function will let u represent g of x, in which case du dx is g prime, and du becomes g prime of x dx. And this is the essence of the u substitution. So what do you do in short? You look for a function and you look for its derivative. What do we mean by that? Let's plunge into some examples. Generally speaking, the more complicated function is a choice of u. Remember the tip. Look for a function u, g of x, and its derivative du or g prime of x multiplied by dx. So I hope you realize, if you're looking at this one, the piece in the parentheses, x squared plus 5 is a more complicated one, so that would be the choice of u. So what happens when you differentiate that? You get 2x dx. Okay. Now I'm going to move the 2x next to dx. You don't have to do that, but it is helpful to see that the entire thing put together is du. So you have u cubed du, which is a simple case of a power rule. Replace it, and you're done. This is the essence of a substitution rule, class. If you honestly understood what happened here, all we do is just practice with various examples. So if you're dealing normally with rational functions and you have a couple of functions, the more complicated one is a choice of u. So here's another example. Can anybody tell us what would be the choice of u? What do you think? Let u be what?
X to the power 3 plus 1.
Beautiful. And therefore, its derivative becomes 3x squared, and du becomes 3x squared dx. Again, I'm moving 3x squared next to dx. It's really a good practice to do that so your reader can clearly see which one is u, which one is du. This whole thing is du, and this is u to the power of 10. So with the proper substitution, u being x cubed plus 1, du being 3x squared dx, pretty much now we have the power rule. This is 1 over 11 u to the power of 11. And don't forget the constant. And replace the u, and you're done. Replace the u, and you're done. Okay, so substitution method. All right. Again, number one, this in front of an integral sign or inside the integral sign, it is just a coefficient and it makes no difference. Now, obviously, this is a more complicated function, and this whole thing, if this is u, this thing becomes du. I hope you see that. So you have the integral of 9u du. So you have the integral of 9u du. Okay, very straightforward. And so with that being the case, it's simply 9/2 u squared plus a constant, replace it, and you are done. Replace it, and you are done, class. So dealing with rational, dealing with polynomial functions, my apologies. The more complicated one is normally the choice of a u substitution, dealing with polynomial functions, All right, when we have a fractional expression, what happens? I don't want to say rational because part A is not a rational expression, part B is, but I'm going to put them next to each other because it's a nice way to compare and contrast. A fractional expression, your very first step should be, can I simplify? If I cannot, then I move on to the next step. This one cannot be simplified. Normally, a good choice of u would be the denominator. So if you choose the denominator to represent the u, I hope you see the derivative of that is e to the power of t. Therefore, du becomes e to the power of t dt. And I'm going to put the dt next to e to the power of t. Not that you have to. I just want to emphasize that we really have them all together. And therefore, you're dealing with du over u. And this is a simple case of a natural log. And you add a constant and you're done. Okay. So that's part A. Part B, you do the same thing. You try to simplify and you can't. I hope you remember that. You look at b squared minus 4ac. The discriminant must be a perfect square for this to be factored. And even if it's factored, it better have a factor of x plus 1 or it can't be simplified. So what do we do? Well, if you let the denominator be the function of interest u, then du becomes 2x plus 2 times dx. You can factor out the 2. So 2x, let me write that at top of that, everybody. So this is 2x plus 2 dx, and we factor out the 2. Now what do we do? There are a couple of choices, and I want to go with the easy way out. The one choice is that, and that's what your text does, they solve for dx. And the more complicated this expression, the harder that methodology. Here's the easy way out. When a number is missing, that means a multiplier, that means a coefficient. All you have to do, multiply by it. So if I multiply this expression by 2, and then I undo it by division by that, notice how I'm going to put that. Take a look. So I put x plus 1 and dx next to each other. I need number 2. Because it's a number, I put it there. What does it mean? I'm multiplying by it. How do I undo that? Multiply by its reciprocal or divide by it. So in essence, if a number is missing, it's not a big deal. You can't do that if a variable is missing. Okay, now again, this is a natural log with a 1/2 in front, and you finish the job by putting the original variable, namely x, back. Now, one of the differences between A and B is that if in part A you don't put absolute value and you put a parenthesis, is fine, because 5 plus e to the power of t is a positive value. It's in fact larger than or equal to 5. But in this case, you don't know. You have to keep it in an absolute value. Now, to see if you remember the old stuff, how would you do? I want you to take a look at A. I want you to look at part A. And I'm writing the reciprocal of part A. How would you do this? Any ideas? What would be your first step if I want to do this integration? Anyone? What would you do?
The old way,
The old way, you're right, which is what?
you have to write 5 divided by e to the power of 3 plus 1.
Beautiful. So you are going to write out two fractions. This is one of it. This is one. This is another one. This gives you 5e to the power of minus 3. This gives you 1. And this doesn't require any substitution. And that's important to see. Because we are learning new stuff, it doesn't mean that we should forget about the old stuff. So having said that, the first one you divide by negative 1 becomes minus 5e to the power minus t. This becomes t. Pay attention to your independent variable and a constant, and we are done. Okay, and we are done. Okay. Again, I have a couple of questions next to each other. The reason why, because I want to explain the following concept. Generally speaking, if you are wow, what can I tell you? Always stay muted. So if you have an exponential, the exponent is a choice of u. So in this case, we choose x to the power of 5 to be u, and its derivative is 5x to the power of 4. Du becomes the same thing times dx. I'm going to put the 5x to the power of 4 next to dx. So this is e to the power of u, and this whole thing all together is du. And the derivative and the integral of basic exponential is itself. You replace the u, and you're done. Finally, you can always check how differentiate, and it gives you this expression without the dx. All right, so that's part A. Part B, the exponent is x to the power of 5 minus 2. Its derivative is 5x to the power of 4, therefore du becomes 5x to the power of 4 dx. Notice I put number 5 in a different color, which means I've got everything here except number 5. So what can I do? I can multiply and divide by it. So take a look. If I put the 5 in, I'm going to move x to the power of 4 to next to dx. Okay. I want the whole thing together. That means I'm multiplying the expression by a number. I undo that by multiplying by its reciprocal. This is the fastest way, class. This is not the only way, but this is the best way. Again, practically you're done. 1/5 e to the power of u and a constant. Replace it, and you can check by differentiating the result. It gives you the expression here without the dx. Okay. So if you're dealing with exponential functions, normally it is the exponent that is a good choice for you. Okay, class? All right. How about here? I'm going to do this slightly different on purpose because I want you to see and be exposed to the way that the text approaches it. So first and foremost, 3x plus 1 is a choice of u. Du becomes 3dx. Okay. And so because this is simple enough, let's approach it that way. Let's solve for dx and do the math. This is not the way I do it. Remember what I do. And number 3 is missing. I put number 3 and 1/3 out. This is the fastest and easiest way. Okay. Number 3 is missing. Put it in and out. That takes care of the business. They solve for dx and they replace it. Granted, eventually it gives you the same, answer. And if you've learned it that way, stick with that, don't change. But if you're learning for the first time, this is a faster way that just put the number that is missing the coefficient and undo it. And of course, square root of u is u to the power of 1/2. We've done this a number of times. Okay, you know how to differentiate that. And as far as the method that I do, remember, number 3 is missing. I put the 3 and then I do it by putting 1/3. So that is the method I go over. And I hope you see this from here to here is a lot faster than going through the process. Now you have to integrate this. Okay, let's just quickly see that we've done it many times, but in case. So when you integrate this, you get 1/1/2 plus 1 u to the power of 1/2 plus 1. 1/2 plus 1 is 3/2, so this piece is 2/3. That's how we get this number, okay? So 2/3. So 1/3 times 2/3, which is 2/9, and you can replace it. If you left it as that, it's absolutely fine, because it gets a little bit more complicated if you want to write it the other way around. You could write it in a proper format, which is the following also. But it's not that big of a deal for a question like this. Okay. So substitution solving for dx is another methodology that they use. And sometimes it's really helpful. It's good to know all methods and see what works best for you. All right. Again, we have a couple of questions side by side. The idea is that most of the time, if ln x is involved, then ln x is the choice of u. Okay. So if we choose ln x to be u, du is 1/x dx. So let u be ln x, du becomes 1/x dx. Okay. And so let's do the replacement. As far as the way you write this class, if you see that this is equal to this, fine, you don't have to rewrite this. If it's hard to see, you want to move the x under dx, so you can write it as 1/x dx, or you want to write it as dx/x, whatever that is easier for you to see that this part is the du, okay? However, it helps. Again, you're dealing with a power rule. 1/3 u cubed and a constant, replace it, and you're done. The only thing I want to add, class, is the following. I want to refresh your memory that this is not, well, let's just write just the natural. So ln of x cubed is not the same of ln x. To the third, please don't mix them up, because the right side means ln x times itself 3 times. This can be simplified to 3 times ln x. Two different things, don't mix them up. All right, look at the right side, look at part B, and rewrite the expression again. Rewrite the expression, class. And so it's 1/x, 1/ln x times dx/x. This part is du, this one is simply 1/u, okay? And Again, you can always go directly to that. I just want to make sure there's no confusion. And when you get comfortable with that, you can stop doing the same thing, okay? So what happens? You get natural log, and you replace the u happen to be a natural log itself, and this is the final answer class. ln of ln x plus a constant. If you want to check, you can differentiate the result. You get this one without the dx. That means you get 1 over x times ln x. Okay, class? 1 over x times ln x. Okay. What we want to look at is when sine and cosine are involved. We want to see what happens. Okay. If the argument has power, that is most likely the choice of u. So let's finish that. We discuss the next one in a moment. So if you choose u to be x squared, then 2x dx becomes du. So what does it mean? Again, we have the same situation. Put the x next to the x, everything is in order. The only thing missing is a number. So, okay, we are in good shape. Since only a number, a coefficient, a multiplier is missing, you can just put it there. That means you're multiplying. You undo that by multiplication by its reciprocal. And so that is a simple case now. And remember, the derivative of sine is cosine. The integral of sine is negative cosine. That's why we get negative 1/2 cosine u plus a constant. Replace the u and you're done. Finally, you can check. All you have to do, differentiate this, and that gives you the answer. Okay. Part B. Anytime you have sine and cosine class, sine and cosine, both of them involved, and one of them has an exponent, sine or cosine, makes no difference. The one with the exponent, the one with the power, is a good choice of u. In this case, I hope you realize that means sine x to the second power. That's the meaning of it. So that would be the choice of u. So take a look. If u is sine, then du becomes cosine x dx. Now, if cosine has a power, then because the derivative of cosine is negative sine, it will still work. Okay? So the one with the power is the choice of u. And again, we end up with a power rule, everybody. And so we get 1/3 u cubed plus a constant, where u is replaced with sine, and we are done. All right. Let's look at a definite integral when we want to evaluate and end up with a number. How do we do that when we need to do substitution? Well, there are two ways. One is that we do the math, we go back to the original variable, and therefore original limits. The lower limit is 1, the upper limit is 2. This is a simple case. Let u be x squared minus 1, du becomes 2x dx. Okay, class? We've seen this, right? And so notice, so it's a simple case. The answer is 1/4 u to the power of 4. We don't write a constant, okay? And I don't have the limits yet. I want to make a point. The point being, okay, we don't need the limits. We can go back to the original variable, namely x, and use now 1 and 2. You cannot use 1 and 2 for u. You can use it for x. Now, if you plug in 2, I hope you realize it becomes 2 squared, which is 4, minus 1, this is 3. To the power of 4 is 81. If you plug in 1, you get 0, so 81 over 4. And you're done. You can always go back. So return to the original variable. Okay, so we had seen this, now we see it with those limits. Now, what if we don't want to go back to the original variable? If not, we have to figure out the new limits. So what happens? Here's the choice of u. Plug in the lower limit. If you plug in 1, you get 1 squared minus 1, which is 0. If you plug in 2, you get 2 squared minus 1, which is 3. So those are your new limits. Okay, keep track as follows. So when x is 1, we get 0. When x is 2, we get 3. And so now you have a choice. You can go with the original limits and original variable x, or now you can use the new limits. And either way, it gives you the same answer. So the point being, if you happen to have a continuous function where we are evaluating it from a to b, f of g of x, g prime of x dx, then the lowercase a is u function or g of a, and the other one is again the u function, plug in g of b. I hope it's straightforward. You don't have to memorize this at all. Just plug in the lower and upper limit into the u function. Those are your new limits. Your done becomes a simple case. All right. Here's another example that requires the substitution. Again, we don't worry about this integration. We've seen it. We should be comfortable with that. We've done it a number of times. So let u be 25 minus x squared. Okay, then du becomes negative 2x dx. So if you let u be 25 minus x squared, du becomes negative 2x dx. Let's rewrite it. First and foremost, negative 2 is missing. Again, since it's a number, I wouldn't worry about that. I just undo that. How? Multiplication by its reciprocal, or dividing by, either way. So multiply by negative 2, divide by negative 2. So here's what you have. Notice I don't write the limits yet, because I want to show you, you can always go back to original limits, then we figure out the new limits in a moment. So square root of u, we've done that class. If you go back to your notes, it's u to the power of 1/2, which is 1 over 1/2 plus 1. This makes it 3/2, and 1 over 3/2 is 2/3. Let's just write it. This is 3/2, and this one, the reciprocal of 3/2 is 2/3. 2 and 2 cancel each other, negative 1/3 u to the power of 3/2. So what can we do? Now we can go back to the original variable, original limits, and do the math. Or let's figure out the new limits. To do that, it's very simple. If you plug in number 3, you get 25 minus 3 squared, which means 25 minus 9 is 16. Plug in 4. Okay. You get 25 minus 4 squared, which is 16. 25 minus 16 gives us 9. So here's the new limits. Lower limit of 16, everybody, and upper limit of 9. Okay. So let's plug in. So plug in 9, plug in 4. I hope you realize this means, okay, this is square root of 9 cubed, which means 3 cubed, which means 27. This means square root of 4. This is 16, class. This is 16. Change this to 16. 16 cubed, which means 4 cubed, which means 64. So 27 minus 64 is negative 37. With that, it gives us positive, okay, class. So it's extremely important to pay attention to the basic math you need to do. Change the 4 to 16, everybody. Change the 4 to 16. All right. Let's look at the next question. Let's take a look at the next question, class. We want to do this, and again, it requires substitution, and let u be the more complicated function, which is 2x cubed minus 8, and the u becomes 6x squared dx. So what is missing? Number 6. So you can put number 6 and undo it by putting 1/6. But what are the new limits? Well, if you plug in 0, you get negative 8. If you plug in 2, 2 cubed is 8 times 2, 16 minus 8 is 8. Okay, class, maybe I'll quickly show you. So plug in 0 and it becomes minus 8. Plug in 2 and you get 2 times 2 cubed, which is 2 times 8, 16 minus 8 is 8. So, okay, so minus 8 to 8. U cubed gives you 1/4 u to the power of 4. With 1/6, it gives us 1 over 24 u to the power of 4. Now, this is an example where it's easier to use the new limits to see the answer. If you plug in, you will, or you can use that, you will get to 0. How do you know that? So take a look. It is easier to use this one, everybody. If you plug in, remember what you get. You get 1 over 24, 8 to the power of 4 minus negative 8 to the power of 4. And what is the exponent? An even, which means 8 to the power of 4 as well as negative 8 to the power of 4 have the same answers. They cancel each other. They give us 0. It is a tad faster using the new limits to get to the result, class. It's a tad faster. So I highly recommend you use the new limits. Okay. All right. Could somebody read this question, please? Okay, anybody feels like reading this for us?
The divorce rate in the United States is approximated by DT, where DT is the number of divorces per 1,000 people, 2 years after 2000. Find the total number of divorces per 1,000 people from 2000 to 2000. B. Same thing from 2000 to 2016.
Thank you so much. This is, class, what's called an accumulated change, okay? Net change theorem applies. The fundamental theorem of calculus, we have discussed that before. So basically, the integral of 0 to 8 is the answer, 0 to 8. And Of course, you can use the substitution, but it's, I mean, you let, if you want to do the substitution, you let this one to be um, u, but there is really no reason for that, okay? It is simple enough. You remember that all you have to do, divide by this exponent. Remember, you multiply by it in the case of differentiation, you divide by it in the case of integration. And this number, obviously, you use a calculator for that class. I'm assuming now you finish the job. You use a calculator, you plug in 8, you plug in 0, and it gives you an answer. You round it because it's the number of the forces, and you want to make it a discrete value class, a countable value. So the total number of divorces per 1,000 is 30, as it appears. And so this is the rate, remember that. From 2008 to 2016, we do the same thing from 8 to 16. You really don't have to redo that. You have this one, put it in here, and just change the limits, right? And again, you use a calculator, you plug in the two numbers, 16 and 8, and you do the math, and you have the answer, okay? So the purpose of this question, just to remind you for applications and using definite integral, we use FTC. All right, let's see what happens here. We want to evaluate the integral. Again, I have a bunch of questions next to each other on purpose because I want you to compare and contrast and see how we do that. So we have a fractional expression. More specifically, all of them are rational expression. Your first step is to simplify if you can. Okay. And when we cannot, so be it. We can't simplify. In fact, for part A and B, the choice of u is the denominator. Okay. And so if u is 1 plus x squared, in both cases, du becomes 2x dx. So let's see what happens. Both parts A and B have the same choice of u. And therefore, when you calculate du, you simply put the numerator. So let's look at part A. What becomes of it? It becomes a case which results in a natural log. Okay, and you replace. By the way, you need an absolute value here, but you don't need an absolute value here because 1 plus x squared is a positive value. Okay, in fact, it's larger than or equal to 1. Okay, so that's part A. Okay, let's do part B by plugging in. And I hope you remember you rewrite this as u to the power of -2, and you use the power rule on this. 1 over -2 plus 1, u to the power of -2 plus 1. So let me just remind you, you've seen this before. So this is going to use 1 over -2 plus 1, u to the power of -2 plus 1, which is 1 over -1 or negative u to the power of -1. That's how we arrive at it, or -1 over u. So -1 over u class, okay? -1 over u. Okay, sorry, the order is not done. We'll see that in a moment. So since the order is wrong, so this one, let me just write that. -1 over u and a constant, and u is 1 plus x squared. We are going to replace that. But for now, let's finish this class since that one. So -1, okay? So we get -1 over u plus c, or -1 over 1 plus x squared. I'll show you in a moment. For part C, the denominator is a choice of u. du is the numerator, and this becomes natural log. And you replace it, and you do need an absolute value because unlike part A, this could be negative class. So so this is always positive, but this could be any number. And again, going back to part B, 1, negative 1 over 1 plus x squared is the answer. Okay. Okay, so that's that. All right. Okay. If we happen to have a symmetric function, okay, it's either odd or even. I mean, there are the two famous ones are odd and even. Even means f of minus x equals f of x. And therefore, even from the picture, you can see that when they are equal, as we go from negative a to a, it's easier to calculate 0 to a multiplied by 2. That's why it's important. I mean, sometimes it really doesn't make any difference. You evaluate from negative a to a, big deal. But a lot of times it makes it easier to go this route, okay? And so you can calculate 0 to a and multiply it by 2. If it's odd symmetry, that means f of minus x is minus f of x. Then, as you can see, the area are equal and opposite in that sense. So they cancel each other. So this area is positive, this area is negative below. And we get it to be 0. Remember, if you're interested in calculating the area, you have to put it in an absolute value class. Remember, if you want the area, you have to put in an absolute value. However, for a case like this, you basically notice that it's the net area, and it becomes 0. So having said that, so f is continuous from negative a to a. If it's even, we have this one. If it's odd, we have this one. A quick proof of that would be if you just separate them based on the properties of definite integral from negative a to 0 and 0 to a, then this part we can flip it over, okay, and write it as such. Everybody remembers that if I flip over the limits, then the sign changes. Okay, so the second part we are not touching. The first part is this. So let's evaluate. Let's deal with this first part. Depending upon the function being odd or even, a number of things happen. So if you look at the first integral, so the second one is fine and that. The first one, if you let u represent minus x, du becomes minus dx, okay? And x becomes minus u, not minus a class. Okay, and so if that is the case, let's deal with the first one and replace everything accordingly. Okay. This is actually this is for the limits class. So if you replace the x, okay, remember this means x, and this is for the limit, so that's fine. So this negative remains. 0 to minus a becomes 0 to a, f of minus u minus du. So if you let u be minus x, if you let u be minus x, okay? In other words, x becomes minus u. So replace the x with minus u, okay? And du becomes minus dx. That means dx is minus du, okay? And therefore, if you go with u being negative x, when you plug in 0, you get 0. When you plug in minus a, you get positive a. So that's how it changes. Now negative times negative times negative, we write that and it becomes, okay, this is f of minus u. This part, class, this part has a negative sign times du, and this negative sign and this negative sign, they give us positive sign. All right, now what? It's either even or odd, okay? So we know this is the answer, okay? We know this is the answer, and now we are changing this answer to this one, okay? If f is even, then f of minus u is the same as f of u, okay? So we are going to replace this with f of u. And remember, u or x is a dummy variable. It really makes no difference if I put u or m or any other variable such as t, they become identical. There are two of them. On the other hand, if it's odd, you replace it with negative. They undo each other and they get 0. Believe it or not, this is the proof. So one of the things that I want to mention, most of the time, it'll help you when the case is odd, class, not even. The even can speed up the process, but odd makes a huge difference. So here's a couple of examples we want to look at. Again, integral of symmetric functions. F is continuous from negative a to a. F is either odd, from the negative a to a, it becomes 0, or it's even and it becomes double. So basically, we are going from negative 2 to 2. By the way, the function may be neither odd nor even. I want you to know that. So if you show that this is even, and I hope you realize why this is even, because this has an exponent which is even, and believe it or not, a constant also even. So you have to show this before you move on. I'm going to assume you can do that. This is an algebra problem you've done before. You prove that, and that means it's even. And so instead of evaluating from negative to 2, we're going to evaluate from 0 to and multiply it by 2. So what is the difference? It's a lot faster. That's all. It's really, but as I mentioned, for even, it doesn't make that much of a difference. This is, so a simple case of a power rule, 1/7 x to the power of 7th plus x, evaluated from 0 to 2. Don't forget there's a 2 in front. Okay, so you plug in. Okay, so the reason you go this route, because 0 makes it 0 and makes it easy to calculate. All you have to do, calculate the 2, okay? Plug in number 2. So 1/2, 2 to the power of 7. 2 to the power of 7 is 128. And you get 284 divided by 7. Okay, so by the way, 2 times 7 is 14 plus 128, okay? So it's just a simple case you can handle. So as you can see, we are evaluating this from negative a to a, namely from negative 1 to 1. And this is the one that really is helpful. This would be 0 if it's an odd function. So yes, it is. It is an odd function. And so basically means replace the x with negative x. Otherwise, it's at this level, it's impossible to calculate its integral. Okay, f of x is tan x over 1 plus x squared plus x to the power of 4. Satisfies that f of minus x is minus f of x. It is an odd function. You have to show that, class, okay? In other words, you have to write f of minus x equals tan of minus x. Why is this doing that? Tan of minus x over 1 plus minus x squared plus minus x to the power of 4. So you must show that. I hope you realize tan of minus x becomes minus tan x. And the denominator remains intact. So this is minus f of x. You must prove that step by step. You must show your reader this is an odd function and why it's an odd function. Okay, this is an odd function and you have to show them why it's an odd function. Okay. You can work on this one on your own, the integral of x to the power of 4 sine x dx, as we evaluated from negative pi over 3 to positive pi over 3. And I think that's question 66. Go ahead and work on that on your own later on. We want to evaluate the integral of tan x. We haven't discussed that up to now. So to do that, we are going to use substitution as follows. First, we are going to rewrite tan. Everybody knows it's sine over cosine. It is a fractional expression. So if you choose the denominator to represent the u is cosine x, the u becomes negative sine x dx. So what's missing is a negative sign. So you can put a negative sign in, negative sign out. Okay, class? Put a negative sign in, negative sign out. And now you are looking at negative 1 over u du. So it's negative, and it's a natural log. And of course, you replace it, you end up with minus ln cosine x. If you left it as that, it's okay. I hope you realize it becomes secant, okay, because you can put this negative in. So it becomes natural log of cosine x to the power of -1, which is natural log of 1 over cosine x, and that gives you ln of absolute value of secant x. Needless to say, we have a constant and it's not going to go away, class. We do have a constant and it's going to stay intact. Okay, we do have a constant, class. So here's the next one. We want to evaluate the following integrals. Starting with the first one, remember, anything involving natural log, most likely ln is a good choice of u. So if you choose u to be ln x, u to be ln x, in this case, ln of x plus 1, ln of x plus 1. Okay, remember, if you differentiate it, it becomes 1 over x plus 1 times 1. So du is 1 over x plus 1 times dx. And therefore, you really are dealing, and remember, this is dx over x plus 1 or 1 over x plus 1 dx. So if we rewrite it, you're dealing with u du, okay? 1 over x plus 1 dx, okay? So you are dealing with ln of x plus 1. If it helps, you can rewrite it in the following manner. I think this is good, but in case, you can rewrite this as ln of x plus 1, okay, times 1 over x plus 1 dx. And now you can clearly see that you have u. Okay, so now one thing I want to add, class, you can stick with the original variables and original limits, go back to that, or the new limits. How do we get the new limits? So let's plug in 0 into this. plug in 0, you get ln of 1. Okay. Now plug in 1, you get ln of 2. Of course, what is ln of 1, everybody? So I put ln of 1 and ln of 2 on purpose because I want you to see what we get. And then I'm going to explain that ln 1 is 0. So this is 1/2 u squared as we go from ln 1 to ln 2, where ln 1 is 0. So the top gives you simply ln, the bottom doesn't give you anything. And you leave it as that because it's a precise answer, class. It's a precise answer. Okay. Now, we have this question. And I figured this is a nice place for it because one may be under the assumption that we need a substitution, but we don't. Part B, I'm looking at part B. I hope you realize that when you look at tan inverse, its derivative is 1 over x squared plus 1. So tan inverse, its derivative is 1 over x squared plus 1. So the integral here is, remember, 6 is just a coefficient. You can even put it out. So you have 1 over x squared plus 1 times dx. If it helps, let's rewrite this, class. If it helps, you can rewrite this as 1 over x squared plus 1. Even 6 goes outside times dx. And of course, I didn't write the limits, but I just want to make sure you see 1 over x squared plus 1. So therefore, you see tan inverse, okay? So the answer is 6 tan inverse, and you have to evaluate it. And basically, it becomes 6 tan inverse of square root of 3. So minus tan inverse of square root of 3 over 3. This is a basic trigonometry. So here we are saying what, arc or angle gives us tan to be equal to square root of 3. It's pi over 3. And what arc or angle gives us tan, which is square root of 3 over 3, which is pi over 6, okay? And pi over 6 minus, pi over 3 minus pi over 6 becomes pi over 6. Multiply it, and you get pi. So this is your final answer. On purpose, I put it in substitution chapter, a section, so because if you are doing substitution, it doesn't mean that, we are always doing substitution. There may be something else, okay? I want to get one more example, although I have more examples that you can look at on your own. I want to look at something that you may not come across often, but the method of substitution in this case, which is going to be different, will do the job, okay? But it's a different type of substitution. So let's see how that works. Again, it's a complicated one, just the way it is. So if you choose 4x plus 5 to be u, then du is 4 dx, and dx 4 is missing, you can put it there. But here's the problem. We also have a x. Now here's the methodology that works. This is again different than a basic substitution you've seen. For a case like that, so this one is square root of u, this one is, you can put du and then 4 out, as I said, 4 in, 1/4 out. So what about x? You should solve for x here, class. X is u minus 5 divided by 4. So this is what I mean. You have to do it completely differently, and it takes a little bit of a time. So take a look at what happens. We are going to solve for x here. I'm assuming everybody has an easy time. Move the 5, divide by 4. Okay, now replace everything. You can do that. Okay, so x, first and foremost, I see number 4, I put 1/4 and 4. Okay, so that's it. Now I'm going to replace the x with u minus 5 over 4, or 1/4 u minus 5/4, whatever. And this one is square root of u. Okay. And so, of course, this is u to the power of 1/2. Okay, now let's do the multiplication. Okay, u to the power of 1/2. Let me just write it at top of it, class. This is u to the power of 1/2. We are going to distribute. Okay, we are going to distribute. So we get u to the power of 3/2 minus 5 u to the power of 1/2. What about number 4? Number 4, because everything is divided by 4, we can take it out, and 1/4 times 1/4 becomes 1/16. In other words, let me do this. This one and this one result in 1/16, everybody. Okay. Now you have a simple case of a power rule. So the substitution is not a normal substitution that you deal with. And so 1/16 remains intact. This is 1/3/2 plus 1 u to the power of 3/2 plus 1 minus 5 over 1/2 plus 1 u to the power of 1/2 plus 1. Okay. So we have this 1/16, you can multiply it at the end or keep it here. It doesn't matter. Okay. So 1 plus 3/2 is 5/2. So the reciprocal is 2/5. 1 plus 1/2 is 3/2. The reciprocal is 2/3. And you do the math. Okay. So the first one, 1/16 times 5/2 gives you 1/40. U is replaced by 4x plus 5. Then minus 5/16 times 2/3 is minus 5/24. U is replaced, and that's what you have.